Unmanaged water across a natural landscape represents raw, volatile power. Engineers must design static, immovable structures to withstand this chaos. These concrete structures must survive these inherently chaotic natural systems for decades without failing. This catchment system blueprint illustrates the data pipeline used to model that chaos. Everything begins with system inputs. Precipitation is the foundational variable for all subsequent modeling. This water dictates the system response, mapped as hydrographs, and system control, which governs flood routing. These complex downstream models carry a strict limitation. If the initial spatial input data measuring the rainfall is flawed, every subsequent calculation is compromised. Precise hydrologic modeling requires rigorous spatial statistical optimization to ensure rain gauges accurately reflect the physical reality of the terrain. Regulatory mandates dictate specific tolerances. Indian standards, for instance, strictly require that the error in estimating mean precipitation over a catchment remains below 10. The mathematical requirement is 5 stations, but our physical catchment network only possesses 4. Bounding mathematical error to safe regulatory limits requires the physical expansion of this hydrologic network by exactly 1 gauge. This hand-drawn sketch translates abstract point data onto the physical landscape, detailing the catchment area. The topographical boundary of this system is the ridgeline. It acts as a high-elevation perimeter funneling interior surface water to a single gauge point. These basins scale massively. The Krishna Basin spans 258,948 square kilometers, tracing water from Mahabaleshwar to the Bay of Bengal. The physical basin acts as a giant geological funnel. It converts discrete, set-in rainfall into continuous, measurable surface flow. The total precipitation is reduced by system abstractions. Water evaporates into the atmosphere or infiltrates into the soil layer, deducting from the total volume. The net effective rainfall that survives these abstractions creates a unique, dynamic discharge curve, forming the foundational signature of the catchment. This chart is the storm hydrograph, plotting discharge in Qmax against time in hours. Before the storm arrives, the system exists in a steady-state condition. This is the base flow. It represents the constant groundwater contribution to the stream, which we must mathematically separate from the storm event itself. When the intense net rainfall hits, the system reacts. Discharge surges upward along the rising limb. Physically, this steep climb maps the rapid concentration of overland surface runoff finally reaching the main channels. The system quickly reaches a critical moment of maximum stress, the peak crest. This peak discharge dictates structural limits. It determines the sizing, capacity, and safety parameters for all downstream hydraulic structures. After the rainfall ceases, the system enters a recovery phase, plotted as the recession limb. The shape of this downward slope is largely dictated by the geological depletion of basin storage over time, rather than the dynamics of the storm. This curve perfectly maps a historically recorded storm, but engineering demands that we design infrastructure to withstand massive storms that haven't happened yet. How do you design a reservoir to survive a 75-year lifespan when the absolute maximum flood is unknowable? Historically, engineers relied on the deterministic approach, shown in the first column here. Deterministic models calculate a probable maximum precipitation and assume the worst-case physical routing through the basin to find a fixed upper limit. This method falls short because it ignores the inherent randomness and extreme variance of complex weather systems. To address that variance, we shift to the probabilistic and stochastic methods, specifically Gumbel's extreme value distribution. Stochastic processes treat peak flows as random variables occurring over time, rather than fixed, predictable outputs. To predict the catastrophic unknown, civil engineers must abandon fixed outcomes and embrace the mathematics of extreme probability. Executing Gumbel's method requires extracting the absolute peak annual flow from decades of historical field data. By calculating the arithmetic mean and the standard deviation of these historical extremes, we build a predictive model. This graph illustrates why standard bell curves fail here. Hydrology curves stretch and skew aggressively to the right, producing a long, flat extreme value tail. Theoretical catastrophic events, like an 18,400 cubic flood, hide far out on this extreme right tail. This location gives us our final design parameter, the recurrence interval. This concept is heavily misunderstood. A 100-year flood does not occur on a reliable 100-year schedule. It is a pure probability. It means an extreme flood has exactly a 1% chance of occurring in any given year, regardless of what happened the year prior. Building safe, resilient infrastructure requires mastering this entire pipeline, optimizing the spatial data, decoding the physical basin responses, and mathematically bounding extreme risk.